Today we will study the ALU. So we have designed a 3-bit ALU that is capable of 6 functions so far: OR and NOR, addition and subtraction. Let's add couple of more things to it. The first is the set or less than the functions. If we recall the MIPS instructions or MIPS instruction set, we have instruction that says that set or less than a comma b, and we are placing a third register C's. We are checking either C's. Number one, if A is greater than or equal to B, then C gets set the value 0. So in order to perform this, I need basically to do a minus B subtraction. That's result. If result is negative, then C is get set 1, else C gets set to 0. So the first thing I need to do is to perform A minus B. So the reason to kind of integration is with because we have already have all the functionality in perform A minus B, so we're just going to leverage this existing circuit and add a little bit more stuff. So everything is going set up just as before. I set B invert, I set up carry I in I and operation co, and according to what comes out of the ALU is A minus B. Now what I am most interested in doing is examine if the result is negative or positive. So I need to look at the carry out coming out of the 32 bit and need to figure out if this bit is 1 or 0, right? So essentially that is what I care about the most. The actual result of A minus B is not interesting, right? So if A is, let's say, 13, B is 17, the result of subtraction is going to a bunch of ones and then a few non-1 bits here. So what I want to put into the register is the number 0000031 0s and then a 1. So all I care about the performing the subtraction, looking at the most significant bit here and moving that into the least significant bit of the result, and everything else it needs to be 0. Okay, so in order to facilitate that, what I do is that I take the result of carry here and I make that's going to be a bit 0 of my result, and all the other bits I have to just be set to 0 and need to be ignore what is coming out at right. So accordingly I need to add new input into the multiplexer, but the input we have 31 is to connected to the new signal less, which is always going to be zeros as so, and bit 0 especially value that comes from carry out of 32nd bit telling me if this is a negative result or a positive result. So what is coming in over here is result of actual subtraction A minus B. I'm going to ignore that and instead I am going to take things result out here, which is bit 0 set approximately. So and the other 31 bit is hardware. Okay, so here is a third operation code for set or less than, which is going to be 1 1, saying that I care about input number 3. So let's set on less than is a simple performing minus B, throwing the most significant bit. It tells me which is positive or negative, making that bit number 0, making all the other bits 0, and then selecting the appropriate result and having that comes out of 32-bit ALU. Now let's also add the next instructions, which is a branch equal to. So the branch is equal to, we are going to compare two registers 1 1 and a label. We have to jump. What I am looking for ALU is a signal that is going to be either 1 or a 0 depending on either values are equal or not. So in order to perform A minus B, if the result is all 0, then I want to 1 come out of this ALU. If the result is non-zero, then I want a 0 to come out of this ALU. So I need to take the result from this 32 bits. After having performed A minus B, I feed it to the NOR gate, and the second signal is basically going to be 1 or a 0. So add to support the branch on equal to all the subtraction, and I am producing a new instruction which is a result of subtraction, 0 or not. So now that we are added all these functionalities to our basic ALU, let's just go back to the control signals and see how this should be set. This is overall the ALU, which it gives us 32 bits. You can use 64 bit, but I'm using 32 bit. So, and the results of are the values with special zero signals, and I will also talk about this. So there is a special circuit that detects what the signal in case of overflow happens. So now look, it just add all the control signals involved. So we said there is an operation code that demonstrates the result is going to come out of the final MIPS, right? So we call that multiplexer at every end. That's why I need 2-bit opcode that needs 4 values to fetch the results. So that setting the 00 means that I'm the result of add. I am taking the result. So it means similarly, if I set 00 and invert the value of A and B, write that to OR. If I'm inverting the value of A and B, if I invert the value of A and B and take the result of AND, that's I am going the NOR function. Similarly, I can do a NAND, but setting this to be 1 and taking the result of OR gate. Then if I want to do an addition, I'm going to set the opcode or operation code to be 10. A and B are fed into their raw form. If I want to subtraction, I am taking the result of adder, but the value of B gets inverted. And the provided a carry in 1, which automatically happening by setting this one. If I am doing a set or less, then again I am performing subtraction, so the value of B get inverted and the carry of 1 provided, but instead of taking the result of A minus B, so what I take the other input to the multiplexer, which is 1 that is a special input, has a 30 bit set to 0, and the last bit comes from the result of the addition or a subtraction, and so it tells me if the result is negative or positive. For a less than, I need a new operation code, but I am essentially doing is subtraction of B from A. Then if I was doing a branch on equal to, I'm again going to perform A minus B, so A is going to be 0, B is going to be inverted. The opcode doesn't really matter, because if I perform a branch on equal to, I don't really care about what kind of result come, but I care about the result that comes from the 0 signal that is going to the output that is equal to, so that I don't care again. We really don't care about what come out of this result. And this is how I would control this basic AL. This kind of finds the heart of microprocessor system, because ultimately a large fraction of instructions are going to perform various kinds of mathematical operations, and all of that is performed on the adder, and we were seeing the external on the adder. The circuit is going to go into this multiplexer and the AND gate, OR gate, integrate the gates, and so on.